Okay, well, thanks for the invitation. I'm very happy to be here. My talk here is multi and physics. So you can figure out this more on the software and application side. Okay, but here's the agenda for today. First, who we are and what we do. This is something important. And we'll go over all this. And I think I spent much more time in this support here. Right. What we are and what we do. This pretty picture here shows well, COPY stands for the Graduate School of Engineering at the Federal University of Rio de Janeiro. Oops. Good. Right. Wow, we have 12 graduate courses in engineering and computer science. I'm proud to say that we have the biggest amount of high-ranked graduate courses in engineering and computer science in the country. And we have 108 research labs. Mine is just one, the HPC Center, just one of those. So, 0.1% of all labs, that's it. And, well, this is our ecosystem. We host in our campus the Petrobras Research Center, which is the biggest one. And a startup incubator with more than 50 or 60 enterprises already graduated. And the Rio Technological Park with more people from Petrobras, Schlumberger, Halliburton, Bacon Hughes, Tenaris, BG, wherever. And 2 big labs, a copy of the Viz Lab where we host our biggest computer, and Lab Ocean where people do actually test things for offshore platforms and offshore activities. And, well, the center, China, Brazil, Tsinghua University is also hosted there. NACAD stands for, in Portuguese, for the High Performance Computer Center, is our center name. Our mission is to provide and operate infrastructure for advanced computer and develop multidisciplinary research and R&D in those things, especially on energy, oil and gas, wherever this listed here. Being in Rio, well, I mean, Rio is nowadays one of the oil and gas hubs of the world, so we do a lot of oil and gas stuff, related stuff. Very recently, we are selected as the first Intel Parallel Computing Center in the country, in Latin America rather, and this was 2 weeks ago. People from Intel, our director there, and announcing this. It's not on the Intel IPCC webpage yet. We sent our data just yesterday to them, so we're going to be soon in Intel's webpage. Okay, perhaps we have discussed this before. This is, the 3 machines in Brazil, and it was guys from NVIDIA Arnaldo who had set the position of the BRICs. I rather did something very more complete, I guess. I plot from the early beginning of the top 500 to, let's say, some people around here, 2009, 10, I don't remember, this evolution of the BRICs. In green, Brazil, red, China, blue, Russia, and orange, India. We see that we start first. There are 2 numbers here. That, I mean, China, it's not, it's not the last one, but the trend is the same. It means that China had 24 machines and has the host number 2 in the world. So, I mean, it's clear that we start earlier than everybody having machines on the top 500. And if you plot this against the economic crisis in Brazil, we see that, and of course, we are behind. We're still behind. As an indicator, we are the worst of the BRICs, right? And that's for sure. But we start earlier than everybody. And today it's important to say that we have a community on HPC and computational science and engineering as well, with well-established conferences. Our HPC conference has been running for 25 years, as well as our computational science engineering conferences. We are in, let's say, in the business for a while, But this is basically for open science. Our position for open science is very, very badly because it depends on massive investments from the government. And well, we all know that this goes like this, with more downs than ups in our case. Anyway, multiphysics, what it is. Well, there's a lot of students here. I mean, yeah, all the students we used to teach you application and things with physics, like a Jack the Ripper approach. We teach you electromagnetics. We teach you, you know, heat transfer. We teach you mechanical. We teach you fluids. Oh, come on, I mean, look at this room. We have temperature, we have flow going on. We are seated, putting pressure on your seats. So everything is multiphysics. Come on, I mean, now we have computer power to solve everything together. Let's have fun. Well, this is a paper on 2013 International Journal of High Performance Computing that say multiphysics system consists of more than one component, what conservation law, well, putting together and communicating to some boundary or some interface. Well, an airplane flying, everybody has, you know, when you look at the wings all, thanks God, they all move. So they are interacting with the flow. So we constitute two different physics. And this is basically what this is all about. I mean, you can read it technically or listen to me speaking to you more informally about this. Anyway, we can you know, you can partition the field, work on a split. It can be doing algebraically in the system of equation or using the underlying PDEs, wherever. There's several ways of doing this. Examples, well, fluid structure interaction, thermal structure interaction, contour structure interaction, solid fluid thermal interaction, fluid structure combustion, blah, 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 and name it. You can really think about particle interaction by, you know, fluid particle, one field, and any particles, whatever you want. I mean, so it's combination and coupling of this. And how can we write software to simulate those things? That's the fun thing. So let's move on. I mean, we have also a wide range of interacting length and time scales at present, which causes difficulties in terms of simulations and on the underlying mathematics as well. There's a lot of strategies. Okay, what do you think? Let's put everything together and solve in a big system. That's the monolithic. There's a partitioning. Your fields are, you know, tried and isolated. You have a code, a very good fluid for a code for a fluid, have a very good code for thermal, and use them, and they exchange information sometimes. Well, both are general. We prefer partition approach because it allows you to use the best components for each physics. But this is not, you know, a dream thing. When we do partition, we may see degradation of time-step stability. Accuracy can be improved by iterating on every field. There's a lot of tricks we can do. I'm going to show some example computations. Those are really real-life computations that we are doing. And this is done for Petrobras. This is computed in parallel, of course. I mean, everything here is parallel. I don't need to say this. You can see this is an example of you seeing this water, air, and the ship under the wave action. This is an example of wave-air structure interaction. Again, this is geology. Is called Petrobras sedimentation tank. They simulate physically how the oil fields are formed, and they came to us to say, well, can you help us to design our physical simulation? This is the opposite. You know, the computer simulations helping people to design experiment. That's cool. So, I mean, this is a tank that people will inject some material. All this has been documented, you see here. Down there, there's a lot of references and stuff. This is an example of fluid, and plus sediment deposition, and this is how it goes. Here come the sediments, and this will form deposition. This deposition will mimic the formation of our offshore reservoir, okay, oil reservoir. Anyway, just to finalize multi-phase flow, this is horizontal permeability. This is an example of multi-phase flow in porous media. What is fun here is, well, we were doing a benchmark and running all those things in our machines. The blue color here means that we are actually allocating 8 core per node. But what happens if we allocate only 4 core per node? We have improvement improvement in performance, which is well, it's bad for someone to, when you buy the machine. Actually, we are paying, well, you pay 512 cores and get worse performance. This is basically due to the competition, between internal bandwidth inside the multi-core processor. This is something that everybody that talked before me is addressing, the need to improve the bandwidth in the multi-core or GPU accelerator. Otherwise, you're going to see this in real-life application ever and ever. Not only us have seen this, we have seen this in but also guys from tech at TerraGrid, they all are in the labs. We kind of, the application community have seen this, and this is why people are pushing to improve the internal bandwidth between the current multi-core and the future generation of multi-core processors with or without accelerators. Anyway, so we've seen that, well, let's examine now how the algorithms and software for computing those simulations, what is behind the scenes, what is under the hood, basically. Well, first of all, let's think about when you say, we are solving a large problem. Hey, come on, what is large? Can be large in size. Unstructured or structured grids with 10 to the power 8 or 10 to the power 9 elements or cells when they are computing, can be large in coupling. We have here many fields interacting. Can be large in physical parameter, have a lot of different physical parameters. Can be large in control parameters. You have to pick up many tolerance, solver options, wherever. Can be large in complexity. You are using several softwares, different software. You need some human intervention. It looks like, now with this human intervention, it bumps into the way we visualize. We're running a complex simulation. We have to visualize on the run and say, oh, it's going wrong, so let's shut this down. It has to be with reproducibility and uncertain quantification. We're going to see an example of this, and of course, data provenance. What we have to worry about besides multiphysics itself? Well, come on. It's all about having efficient algorithms and solvers, data structure, data storage, and data management as well, parallel mesh generation and adaptivity, and of course, visualization. In order to attack these complex problems in science engineering, we have to bear in mind all this. Modern simulation software is complex. You've seen about the simulation I have chosen you with multiphysics. Well, it's complex. We have to resort to implicit numerical methods, which means solving large nonlinear system, computers, adaptive methods. What I mean adaptive methods is method that put the points in your grid where the action is. So it's in terms of parallel computing, it means repetition on the fly. That's tricky. And multiple, of course, couple physical process. Of course, there's a host of existing software library that excel in various aspects of this complexity, and we have to leverage this software whenever possible and being the most efficient as we can. Okay. So everything here multidisciplinary, and okay. Let's look at a single simulation code. Any of those single simulation code that have these major components. We somehow generate your data, input your data, do the time integration. We have inside a nonlinear iteration loop, your former system for linearized system of equations, solve your system of equations. You do more iterations nowadays, update your timestamp, update your results, does post-processing, and later visualize if you have enough space on disk to visualize. Nowadays, we are putting this here. The complexity of all this is order of n or the power 4 over 3, which means optimal solver requires order of n work per time, and accurate time integration is order of n over 1,000, or 1/3. Sorry. Which means the only way that you have to, the only way to improve all this is putting the points where they're needed. So we're talking about adaptive mesh refinement space and time. That's the consequence of all this. And since we have multiple physics, who the hell says that we have to point for a particular physics in the same place? You know, if the action in the fluid is here and the action in the thermal is here, have to be points in two different places. Then we're going to see these examples here. More than this, okay, methods, unstructured grid methods, they also put some nightmare for computers, for current computers. They have discontinuous data. They do gather schedule operations a lot. They have random memory access and data dependencies. That's cool. So we have to cope with this and be efficient coping with all these things, right? And all the data structures we have are grid-based. We have a mesh, we can build a graph, and this is a picture of the matrix. Come on, again, for the students here, why in the hell do you have to study graph theory? Okay, this is a finite difference grid. This is a dual graph with the cells. This is a graph with the points. You have an unstructured grid. You have the dual graph with the cells or elements. You have the nodal graph, and they all resort to the picture of a matrix. Well, I mean, parallelizing this is minimizing edge cuts. So come on, I mean, you have to think about, you know, remember, why in the hell do we have to study graph theory? This, you don't understand any application, parallel computing application, without resorting to the abstraction, to the graph theory abstraction. When you think about a matrix, a grid, wherever, we have an underlying graph, and that dictates your parallelization strategies. No matter in the hierarchy, if you are in the cluster, inside the node, you always come back to this. Okay? So, what is our playground? This is our developed copy. It's a fluid flow free surface FSI, fluid structure interaction solver that do problems like this and have all these things inside it. I will not read it for you. You can read it for yourself. But anyway, I will go for one of those topics. This is, everything has been built by our students and postdocs. Of course, we need a certain, we have internal and external software stack. This is, you know, in green is 30-part code, in blue is homemade. We have a graph partitioning here, Matrices or Scotch. This comes from France, from INRIA. This is from University of Minnesota. Well, I mean, they are the best graph partitions available and can do dynamic graph partitioning. And although we interact a lot of visualization, particularly with ParaView, this is also external. And interesting that we also interact with, this was developed at home, but is a workflow manager in Provenance by Chiron, and you understand why we use this in a moment. We also do adaptive mesh refinement with lid mesh together with our friends from UT Austin. And is an interface which is, well, we have Matrices here and libraries like PETSCI and LastPack inside the software, and allows you to do adaptive mesh refinement. Okay, I will jump to this. This is way too technical in this conference, but I just would like to show you, this is a problem of, you know, a very small problem, but say that just, this is a live table showing, which means importance of adapting the solver and adapting the time step. And by being smart, those procedures are 1 hand long. You can accelerate your code compared to the worst thing you can do, almost, to almost 3 times. Just by being smart, pick up the right algorithms. Nothing to do with parallel computing, but being smart. Okay, and how we do parallel computation at all? Distributed memory parallelism. You take a mesh and give it to a partitioner. One partition keep the data parallel forever. We never concatenate, and data live in their processor. And we have, you can synchronize this. More or less, you take a mesh and split. And yeah, this is a car. You split in 4 and send it to 4 guys and communicate with MPI. Well, a code. Where do we have a threaded parallelism. We have a contention for this because everybody sends information to this. And you do, again, a thing on the graph. You color your graph in order not to have end process within each color. So there is no common grid point on this. So we have no data dependency at all. So this is how it looks like. When we do hybrid computations, we can run on the edge of a graph, doing mesh coloring and exchange information using MPI. Well, that's how things are built inside those application codes. And you can do, collective communications and optimize collective communications, but it's far more efficient to do point-to-point P2P subdomain communications, and where you build, again, a communication graph and store information on who communicates with who. Suppose that you have to update and change your mesh, you have to update all this graph partition and wherever. Have to update your coloring, or update your partition, update your communication graph, and blah, 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 and keeping on updating all these graphs. As an example, we'll give you a very big fluid thermal problem. This is the communication graph. How complex it looks like. The arrows indicate communication direct in sending and communication in reverse and in receiving. And then there is a common profiling tool, tuning and analysis utilities for University of Oregon, that we used to see that, well, with this code, we have flat, and we are spending time on matrix vector products and basic linear algebra, doing parallel computations on the basic kernels all the time. So that's why those things are, you think about visualization, abstractions, whatever. In the end, you spend your time doing, well, SXPY, computing dot product, doing sparse matrix vector multiplications. That's life. I mean, this is what it really is behind the scenes. You have to have this very efficient, otherwise you're going to be killed. Again, this is a demonstration, the same problem, that allocating 8 by 8 in 64, forward 16. This is much better. This is due to contention in our processors. This is more complicated, but I selected a problem that very typical on level set method, just to show you how things get complicated when your points follow. The idea is you have only action here, so you have to have a very high resolution around this point, and this is nothing happening. So I mean, you have to follow this sphere. So you have to repartition on the fly. This is how the mesh looks like, following the evolution of this problem. And yeah, this is just for visual purpose. This mesh that has more than 1 million of tetrahedra and partition in 8, just for, or 16, I guess, just for you to see the colors. We are repartitioning from time to time. And of course, it has a strong impact on the performance of your solvers. And this scale very well. Okay. This is, again, a demonstration problem with adaptive mesh refinement. And I will jump. Oops. Yeah, again, a movie. This is actually a gravity current. This is a more complicated version of all this. Again, this is not important. I will jump on this. Getting bigger and bigger in 5 minutes. Right, this is interesting. We have a mesh for the fluid around the platform, and we can go to 9 billion cells in 200 seconds in 4,000 cores. The question here is not to generate 9 billion, it's generate 9 billion cells in only 4,000 cores. Right? This was run at Easton Pitt at UT Austin. And then comes the other question. I mean, how in the hell can we visualize this? The data was in Texas, we are in Brazil. So, I mean, that's a problem. I mean, the visualization now is really a problem. And, well, this is visualization, what we do in visualization. Look at this picture here, this car here. This car here, you can find this at where? You can find this at ParaView website. We interact a lot of those guys. One of the most popular visualization software, parallel visualization software. And we are thinking about interaction by trying to use our tiled wall display that is powered by a TEC display cluster, and using the provenance database in order to figure out how to interact with this remote visualization, trying to do in situ visualization. I don't have time to go over this. This is thing. And well, okay, if your things are small, keep data where you are, but the things is huge, data cannot be moved off the system. By the way, if you're running an actual simulation of this in a flow problem, this computer platform, but with just 1,000 time steps, I'm talking about something of order 100 terabytes of data. So, I mean, just 1,000 time steps. If you think about this, those things are turbulent. You have a very small time step. 10,000 time steps is something that is really, you know, something that you could expect. And we're talking about petabytes of data. So data has to be there, and the image here and the moving here with us. All right, just to finalize things, I would like to tell you the new frontier. We have X, Y, Z, time, multiphysics, and now everything is stochastic. We don't need to run just one time a simulation. We need to run thousands of simulations. That's the fun of it. So, I mean, how do we explore this? Okay, we are doing this. This is a current, and, you know, I mean, but the idea, the strategy here is have a submission portal. We have a HPC schedule. Every instance of our scientific workflow management system, could be Chiron or Psycumulus, run and takes care of a parallel job with a sample in stochastic space. And we store data on the provenance database and query the provenance database to see what's going on. So we can take control of fault tolerance if the simulations are going well, and give information along with the simulations to the analysts. It is depicted here. We have sample 1, sample n, right by Chiron, and here is domain decomposition running on at this 2-level job level, on the sample level, taking care of a controller scientific workflow management system, and every sample by per se is a parallel job. So this is the exhaust exascalar machine, just like this. Okay, as a proof of concept, well, this is the sparse grids, meaning that we are integrating something in the stochastic space. If we do a sequential time, is 200 days, use a very small machine, 100 jobs, basically, we do it in 24 days. And well, we can provide the geologists want to know the mean of deposition for the two species. And believe me, the geologists look at these things and say, wow, this is happening. Okay, this is happening. This and this are happening, and they are happy to do. But the key thing here is to establish correlations. This sand that's in that deposit here, how it's correlated with this in this point for this particular granulometry. That increases the feasibility and of their simulations, and we are on the verge of doing decision making. We are providing the geologists with things that are more reliable and more, in a way, they are more, let's say, prone to happen. And we have here correlation and risks, and trying to minimize risks. To finish, as Brian is just telling me that it's time to finish, we went very briefly to multiphysics. We highlighted how advancing algorithms and solvers pay off, have to invest on this. Communication is still of paramount importance. Every time you do adaptivity, we have an extra layer of complexity, needs repetition. Mesh generation is still a problem. And visualization, when you have to visualize things, try to avoid moving data around. And we have a perspective of in situ visualization for large-scale problems, particularly, but we have to take care of provenance of data to help in the way. And of course, stochastic multiphysics, as we have seen, is a new frontier, and we have to manage the complexity of sampling the stochastic space, and the uses are becoming more computer science again. Data management, fault tolerance, data provenance, etc. And just to finish my last slides is acknowledge a bunch of people who really do hard work, and our people that support us. Thank you for your attention.